Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh to all my students in Kuwait. I hope you guys and your family are in a good condition. Today we would like to continue our lesson for chapter 4, probability and statistic. So we just continue from the last week class. We stop at the probability calculation for the normal distribution. Okay, from table 4.2 you can see a variety of the distribution with respect of a different application and also the mathematical representation itself. Here we have our normal, log normal and Poisson graph, which represent a different application and a mathematical representation. For example, for the normal, we use this kind of distribution mostly for represent for the physical properties. They are continuous or regular in time or space, and variational due to the random error. So you can see from here the probabilistic calculation is calculated from here. They have got the exponent function here. So also similar with the log normal and Poisson, which represent a different shape of the distribution. So the standard deviations are commonly used as statistical parameter is defined as the square root of the variance. So this is a basic knowledge from you guys. What is the standard deviation? Is the square root of the variance. So that is the units and the formula for the standard deviation. Okay, now we so continue from a table 4.2. We got also a wet bull and also the binomial. Mostly we use the wet bull distribution in order to determine the Factic test. We want to know the cycles effect of the material, for example, and then we have a binomial also, describing the number of occurrence of the particular outcome during an independence test where the probability of any outcome is the similar. Okay, so we just continue. So now we go to the normal, the standard normal distribution. Okay, the PDF, the probability density function for a random variable. X is a random variable. Please remember that having a normal distribution is defined of this one. So this is the general formula for the PDF. Okay, where x prime here is defined as the true mean value of x, and the sigma square is the true variant. Px is depends on the specific value of x prime and the sigma square. The maximum of Px occurs at x is equal to x prime. When x is equal to x prime, from here, so we got 0 here, so exponent 0 is equal to 1. Okay, this indicates that the absence of the systematic error at the central tendency of the random variable having a normal distribution is towards its true mean value. So the variance reflect the width of or range of the variation of Px. So that is the normal basic understanding for the PDF in a standard normal distribution. So now this is the distribution, the normal distribution curve with respect to the Px again the x, right? So if x is similar equal to n equal to mu equal to sigma square, notice that P, okay, with these conditions, with this time interval, with the time limit, is equal to P negative C z equal to greater than C. So this is level of the interval that you need to consider on that. Okay, so the normal random variable, there is a 3 condition here. So there is a probability about 68%. That is normal random variable take within one standard deviation of its means. So that is the one standard deviation of its means. However, for the 95%, there is a normal random variable takes a 2 standard deviation of its mean, and also same goes to 99.7%. That's the normal random variable takes value within a 3 standard deviation of its mean. Okay, So now we go to the example in order to more understanding according to the table provided to you. Okay, using the probability value in table 4.3, okay, that if given to you, no need to worry, shows that the probability that a measurement will yield a value within x prime is plus minus sigma, which is this is your interval, your probability interval, okay, which is in 0.6826 or 98%, 0.26%, 98.26%. So this just want to just to teach you how to read the table properly. So assumption, this is the normal distribution function question. So now find a p x prime minus sigma less than and then x prime plus sigma, which is according to the question above. Okay, so from that you just go direct when you refer to z1 is equal to 1, so you can read directly the z1 is here. Z1 is equal to 1 is along the probability of 0.3413 according to the table 4.3, right? So now, okay, the solution to estimate the probability that a single measurement will have a value within the sum interval. We have the interval before this, right? So we need to solve the integral from here. So this is the normal equation that you need to involve. Okay, so table 4.3 for z1 is equal to 1. We find that pz1 is 0.3413. See from here. Okay, 1. So pz is equal to 0.3413. Okay, so however, since z1 is equal to x1 over minus x prime over sigma, the probability that any measurement x will be produce a value within the interval. Yes, correct, because we got the interval plus minus that before, right? So this 34.14 is only for the positive side. Since the normal distribution is symmetric about x prime, the probability x will be fall within the interval defined between negative into a positive side. So that's why you need to times by 2 here. So this is from the positive side. So because we talk about the normal distribution, we need to consider the interval itself. So from that we have a negative side and also the positive side. So you need to times by 2 in order to get the whole probability function of the normal distribution. So that from that you can get from the graph, you can say that they will equal to 0.6x26, which is about 68.2%. So accordingly, if we make a single measurement of x, the probability that the value found will lie within the interval, okay, which is about 68.26%. So that is the how they are calculate for the probability functions percentage according to the table of the normal distribution. Okay, so now we have another example. This I think I just leave it to you guys to do and then try yourself at home. This is the DIY assessment. Do it yourself at home. If you have any question or you can't get the answer, you can't understand the answer, the question, please come to me and or email to me, and we will do together for more understanding on that. Okay. Okay, so now we go to the statistic of the finite size data set. Okay, statistic of finite size data set. Okay, it means that when you refer to the topic, this is about the statistic, and one more thing about the size data. Okay, so predict the behavior of measured data x based on a finite size sampling of x. Means that you have your plenty of the size. It depends on the conditions of the measurement. Okay, by comparing the statistic from the sampling to an assumed probability density function for the population. Okay, suppose we examine the case where we obtain n measurement. Okay, you have some problem that you need to obtain the n measurement of x. Okay, but for each measurement representative by xi, where I is equal to 1, 2 until n, right? Okay, in case where n is not infinite or does not represent the total population, the statistical value calculated from such finite data set are only estimate of the true statistic of the population of X. We will call such statistical estimate the finite statistic. Important point, whereas the infinite statistic describes the true value, true behavior of the population of a variable, finite statistic describe only the behavior of the sample set. So the point that I want to highlight here is the difference between a finite statistic and infinite. You need to know, differentiate what is the difference between finite and an infinite. Right? The finite statistic describe only the variable of the sample, only the variable, the behavior of the sample. The behavior of the sample. However, for the infinite, is describe the true behavior of the population of the variable. So have a difference between true behavior and only the behavior of that. Okay, so the finite size data set provide the statistical estimate known as sample mean value x bar, the sample variance x square, and the outcome. The sample standard deviation x is defined as this is how, if you have the finite data, you have the finite size data, the plenty of the data, you need to calculate for the mean value. You need to calculate for the variance of the data, and also of course the square root of the variance. You will get the standard deviation, and this is the general formula that you need to remember, and you need to understand more. And then the definition, when xi minus of x bar is the mean value, right? It's called the deviation of the xi. The sample mean value provide a most probable estimate of the true mean value. So the degree of freedom V in a statistical estimate equate to the numbers of data point minus the number of previously determined statistical parameter used in estimating the value. Okay, that is the general understanding that you need to understand. So let's continue. The relation between the probability and infinite statistic can be extended to data set of finite sample size with only some modification. Okay, before this we talk about the finite sample size, right? So how do we want to determine the probability with the infinite position, in the infinite condition? Okay, when the data set are finite or smaller than the population, then Z variable does not provide a reliable weak estimate of the true probability. I repeat again, when the data set is finite or small, the population is smaller than the population, the variable Z does not provide the reliable weak estimate of the true probability. However, the sample variance can be weighted in a similar manner so as to compensate for the difference between the finite statistical estimate and the statistical based on the assumed Px. For the normal distribution of X about the sum sample mean value, we can state that the statistical is mentioned by here, where the TV here provide the coverage factor used for finite data set and which replace the Z variable. So the new variable referred as a student, for example, for the student variable is equal to this equation, when the interval plus minus interval here represent a precessional interval, give a probability P percentage within which one should expect any major value to fall. So this is the knowledge for you in order to understand how the infinite statistic is calculated in a probability. Okay, so we still are in the normal distribution. Okay, so now this is the example for the student T distribution that I mentioned to you before. This T here is represented by this table. Alright, so that's the example of that. So now we go to the standard deviation of the means. Okay, we know already what is the standard deviation of itself, and also we know how to calculate the mean. So supposedly we were to take the n measurement of X under fixed operating condition. So the condition similar like before. But if we duplicate this procedure m time, we have a second we have our second step, which is we duplicate the procedure with m time. We will calculate somewhat different estimate of the sample mean value and sample variance of each of the m data set. Yes, why? Why? This is because the change occurrence of events in any finite sample fact the estimate of the sample statistic. So that is the answer. Fact, the estimate of the sample statistic. This is easily demonstrated. Okay, so we look at the example. From the n replication on the n measurement, when you have your replication activity for the previous one, we could compute a set of mean square, correct? We will find that the mean value will themselves each will be normally distributed about the some central value. In fact, regardless of the shape of px, assume the mean value obtained from the m replication will follow a normal distribution defined by px bar. This process is visualized in figures 4.5. The amount of variation. So from here, from the figures 4.5, what you can see that the amount of the variation possible in sample mean will depends on only two values: the sample variance and also a sample size. The discrepancy tends to increase with the variance and decrease with the n half. So this is, you can see that for a different set of different time of the m will be taken during a process, you can see they will show you a different variations of the mean, right? Okay, and then the normal distribution of the sample without a true value in the absence of the systematic error. Yes, because of the systematic error. But the most important thing, the conditions of this situation is because depends only two value. You need to remember these terms, which is because of the variance and also the sample size during your taken the result, the data results. Okay. Okay, we continue more on that. The dispendency, the tendency between a small sample set to have somewhat a different statistic than the entire population from which there are samples should not be surprising, for that is precisely the problem inherent to the finite data set. Okay, so the variation in the sample statistic of each data is characterized by the normal distribution of the sample mean or about the true mean. So the variance of the distribution of mean could be expected, can be estimated for a single finite data set through the standard deviation of mean. So for the different mean value, you will calculate the variance of the distribution of the mean value calculated for a single finite data set using this kind of formula. When you have your x here is equal to xx, okay, your standard deviations is divided by your total number of sets square root on that. Okay, so from the graph figures 4.6 show how good is estimated of true mean of the variable base of finite size sample. The standard deviation of mean represent a measure how well a major mean value represent the true mean of the population. So from here you can see that the relationship between the sx and xx here and the distribution of x between the xx and the true value. So you can see that the distribution is almost similar in terms of the mean and also the true mean of the populations. Okay. Okay, the extent of that, the range over which the possible value of the true mean value might lie on the some probability level p based on information from the sample data. So this is how they calculate for the true mean. X plus with TV. What is the TV that I mentioned to you before, where TV PS X bar express a confident interval of what the mean value. This looks like the error factor of the probability, which coverage factor t at the assigned probability p% within which one should expect the true value of x to fall. Okay, this confident interval is the quantified measure of the random error in the estimate. Okay, I repeat again, this confident interval is measured of the random error in the estimate of the true value of variable x. Okay, and then the value of xx here, okay, represent the random standard uncertainty in the mean value. I know you are quite confusing because they have a lot of a lot of the derivations and a lot of the definitions for every different conditions and different situations of the distribution. So no worries about that. We just want to make sure that you understand on that, you know how to differentiate for different distribution itself, and that is more than enough for you. Okay, so this is how they calculate. They calculate for the mean value, the true value, based on a finite data set of each data. Okay, okay, so they got the example from here. Okay, I pass to you guys to do at your home. Do it yourself, and if you have any problem, please tell me, so we can do it together in order to get the final answer. They got the solution already, so just go through one by one, and then you can you can try to understand by yourself. If you have any problem, just inform me or email to me. Okay, and now we want to go to the next section, which is about the regression analysis. Before this, we talk about the normal distribution itself, and they have a lot of conditions that involve in the distribution. So from now we go to the next section, which talk about the regression analysis. What is the regression analysis about? Okay, a measured variable is often a function of one or more independent variables that are controlled during the measurement. Okay, a regression analysis can be used to establish a functional relationship between the dependence and independence variable. Okay, regression analysis assumes that the variation found in the independent measured variable follow the normal distribution about each exists value of independent variable. Okay, they got the assumption here. Okay, one of the regression analysis is the least square method. I think the least square method is quite familiar for you guys. I think you heard about this one before this. This method attempts to minimize the sum of the square of the deviation between the actual data, the polynomial fit of a state of order, by adjusting the value of the confidence. Okay. Okay, why do we need to perform the regression analysis, or why we need to understand the regression analysis in the measurement? So when the data collected are obtained over the range of the input value. So from here you can see that okay, the measured data you got from any measurement, you got the point here, right? So when you plot the curve fit in order to get the accuracy of the data, you will get this kind of line graph. So when the data are obtained over the range of the input value, okay, when your data is different instead of the curve fit that is measured, so we need a regression analysis in order to improve our data in a measured term. Okay, so this is how the regression analysis is work. Okay, distribution of measured data value of y about each fixed value of independence of x. So the curve of yc represent a possible function of relationship. So the explanation of this graph will be mentioned here. Okay, curve fitting is passing a function curve between a data point trying to obtain a best fit. So that is the normal practice on that. For example, for the common choice of the function is the polynomial is this. Okay, in the least square procedure, we minimize the sum. In the least square procedure, we minimize the sum or square of the difference between experiment data point and the curve value of Vci at the same location. The goal of this method is to reduce d to a minimum for a given order of polynomial. So from here you can see that for every point they calculate the different distribution at y term, right? You get the y x1, x2, x3, and blah blah. So the point of here is used in order to form the polynomial itself, and then the procedure will minimize in the step is purpose is to minimize the sum or square of the difference between the experiment data. So you want to get the accuracy result to obtain the best fit of your data. That's why you use the regression analysis pointing of your line here. Okay, so the goal is to reduce the d, this is d, okay, to a minimum for a given order of polynomial. Find the minimum where d is equal to this. Okay. Okay, what is D is about? Okay, the method of least square, attempt to minimize the sum of the square of the deviation between the actual data and the polynomial fit of a state order by adjusting the value of the coefficient. So the method of least square attempt to minimize, the function is to minimize the sum of the square of the deviation between the actual data and the polynomial fit of the state. So this is the polynomial fit that you want to undergo, and this is how you fit the polynomial equation according to the fitting of the line, the fitting of the point line. Okay. Oh, sorry. Okay, this is how you calculate for adjusting the value for the coefficient. So the goal of the method of least square is to reduce D, right, as I mentioned to you before, to a minimum for a given order of polynomial. D is the submissions of your polynomial of your data. Okay. Okay, how to select the polynomial order? You got a lot of polynomial order. You got a fourth order, sixth order, and more than that. So unfortunately, how you want to select the polynomial order? So there are no clear rule for the best polynomial order. So it depends on the conditions. It depends on the data collecting during the measurement. Generally, choose between second to fifth order. Okay, to hide and order create curve that are too wavy. Okay, in the extreme, a polynomial of n minus 1 order will pass through each of the n data point, which is clearly not too intense of curve fitting procedure. So you can see the difference. If you select the fourth order, okay, and you select the third order, the highest order create a wavy of the curve of the data line. Okay. Okay, we just continue. So that is how you calculate for the differentiation of the value of D. Okay, you must remember you need to reduce the variations of the D of your regression data. Okay, so this is how they calculate for that. So we'll go through the example after this. Okay, often in engineering measurement, the independent variable is known as the control value. In such case, we assume that the principal source of the variation in the curve fit is due to the random error in the dependence of the measured variable. Yes, correct. The choice of the actual orders of fits used is always compromised between the reducing the random error, the fits, the problem physics, and the convenience of the using the lower order polynomial. So this is how you calculate the just to inform you that using the actual order of fit is used to compromise between the random error, okay, fit in your analysis in your input data with the problem physics and the convenience of your problem using the lower order polynomial. Okay, this is how the example that we can refer together. So the following data are suspected to follow a linear relationship. Okay, this is the linear relation. Find the appropriate equation of the first order form. So you have your value of x, and this is your input, and this is your dependence variable. Your measured variable is y. So this is your total, and your number of your step is will be 5. Okay, this is correct. So now you need to form the formula of this according to the data provided, which is y is equal to a naught plus aix. So your task is to look at what is the a naught and what is the what call it, ay here, ai here. Okay, solution. So we seen, okay, the polynomial. So this is the D that we talk about this more before this. Okay, so now in order to find the a naught and not a1 a naught and a1, we need to use this find of equation. So from that, the delta xi over times by yi, you can calculate it from this formula. Okay, you get from this number and then substituted it into the equation, and then you will get your A0 and A1 is equal to 0.02 and A1 is equal to 1.04. Okay, so this is a formula that you can use in order to get the relation of the linear relation of the data. So but you need to do yourself. I hope you can try at your home. Calculate, substitute all the value here from here. If dimension of the delta here, so means that you need to add all the data here. This is plus plus, and then calculate it, and you get this kind of data. Okay, this kind of result. Please try at your home. If you will not get answer, please tell me and we can do it together after this. Okay, all right. So now the question is, can we define a sample mean and a standard deviation in a curve fitting? Right, so we have our sample of mean and also a standard deviation. Can we make a curve fitting in the collected data, in the measurement, in the measured data itself? So the answer is yes. The curve itself represent now the sample mean within the whole range, because you collect for the mean, you collect for the standard deviation. It means that you collect within the whole range. The sample standard deviation is now called a standard error. So this is how you calculate your standard error using this kind of formula. Okay, now we go to the linear polynomial. Okay, for R is less than plus minus 0.9 or greater than plus minus 1, a linear regression can be considered a reliable relation between y and x. The value of r square is often reported, which indicates how well the variance in y accounted for the fits. So they use the calculation for the r square in order to see the curve is fit accordingly or not. However, the correlation coefficient and the r square value are only indicator of the hypothesis that y and x are linearly related. They are not effective estimator of the random error in YC. So you calculate for the r square value. It's just for you to know the hypothesis that y and x is a linear related each other, not to determine the effective estimator of the random error. Okay, so you need to remember the r square value is just used in order to know the y and x relation are related or not. They have no effecting of the estimator of the error. For example, here if r square is 0.99, when you have your curve, you have your data and then you plot the curve, right? So when you check the r square data, the r square results, they form the r square is 0.99, which indicates that 99% of the variance is y is accounted for the fit, whereas only 1% is uncountable. Means that the related linear between y and x is almost 99% fit, but only 1% is uncountable. This value suggests that the linear fit is reliable between x and y. So the random error between the data and this fit is quantified through the xyx. So this is how you calculate for your random error using this kind of formula. Okay, this is how they calculate your percentage interval for your r square, the confidence level of that. So this is in the linear. Okay, wait, example for any compute the relation between coefficients. Okay, this is the example for you to try. Okay, compute the correlation coefficients and the standard errors of the fit for the data in example 4.8. Okay, example 4.8. This is example 4.8. This is the data that you are given to you. All right, estimate the random error uncertainty associated with the fit and state the correlation with is 95% is a confident interval. So this is the example for you. You can try and then try to compare the result that you got. And then if you have any problem, and please let me know, we can do it together later. Okay, so this is example for the relations, for the linear relations, not the linear relation with different functions with respect to the methods for in order to plot in the graph, right? It depends on the conditions and depends on the situation of your data collected. Okay. Okay, so this is the choice of this. I think we just continue of that. You just can try to have a look by your own and then try to compare different functions of the graph with respect to the difference of the parameter in the graphical methods. Okay, I think that's all for topic 4 for you guys. This is the basic understanding for you guys in order to know the effect or the beauty of the probability and statistical side in measurement and instrumentation, because this is the one big topic that very near with the measurement, because if you want to get the correct, you want to get the accurate measurement, you need have an analysis. So the analysis is come from statistic and also the probability. So you need to understand, you need to know what type of the analysis that you want to do with respect to your problem itself. So I think that's all from the chapter 4. Thank you for your hearing and for your understanding and for your commitment. I hope you guys can understand more, at least a little bit about the flow of the analysis in a data collection. So for your information also, I will construct one e-quiz for you guys in order for you to for your assessment. E-quiz will be e-quiz 1 will be covered chapter 1 until chapter 4, and I will announce to your UKM folio. I know you can access your UKM folio already, so please check the announcement that I will make after a few days after that, and then I will give you the detail about the e-quiz 1 in UKM folio. I think that's all from me. Thank you very much to all my brother. Keep in safe, and assalamu alaikum warahmatullahi taala wabarakatuh.